Today, Dennis has kindly agreed to introduce our speaker, and then we'll get into the world of formal demography.
Great. Thanks, Josh. So I'm delighted to introduce Arni Rao, who's an associate professor at Augusta University. Dr. Rao is a mathematician and mathematical demographer who's worked on many problems of interest to population scientists, including the theory of stationary populations, modeling the dynamics of infectious diseases like HIV and bird flu, and even reporting errors on surveys and demographic data. And so, in addition to his contributions to demographic theory, he's worked closely with policymakers in India to apply his insights to important problems like planning for disease outbreaks and national identity card programs. His talk today is about classical population dynamics, and I think first Jim Carey wanted to say a word or two to introduce us.
Yeah. So I'm Jim Carey. Those of you who don't know me, I'm an entomologist at UC Davis. 35 years ago, I audited Ken Walker's course right here in this room to learn about how real demographers deal with demography. And what a great investment of my 2 days a week coming down here. But anyway, I was at the Nathan Keefe Memorial colloquium here 3 years ago or so at Ohio State. And I presented a talk that included this discovery I had made a few years before that on this light table identity that you'll hear about just shortly. But before I sat down, Arni Rao, I had never met him before, he had pretty much had a theorem and proof done before I sat down. So anyway, he introduced himself after that, and so we hooked up, and over the last 3 years we've been collaborating pretty much online. But now I flew him out just so we could talk more extensively, and also he could present here. Look, he's a mathematician of the highest order, believe me, and but he needs to change his math so that people can understand it. He's a mathematical demographer. But anyway, with that sort of background here, I guess Arni could go. By the way, I want to introduce to my graduate student, Sarah Silverman, who I think is going to be auditing the course here. She'll be the second, what I call myself, actuarial entomologist. Okay, sorry. But anyway, Arni, why don't you go ahead? Yeah.
Thank you, Dennis, and thank you, Jim, for introducing me. And I want to thank SEDA at Berkeley for inviting me to give this Brownback seminar. Thank you, Dr. Josh. Thank you, Josh. Yeah. So the title of the talk, as you see, the classical population dynamics to the dynamics of life left and life lived. So as Jim was mentioning, I'm really touched by Jim's support to these mathematical ideas. As Jim mentioned, I met him at the Nathan Keefe 100 years Sentinel birthday conference held at Ohio MBI, and then that is where first time we met. And then when he presented his talk based on the captured data, and then he was telling this sort of new problem, this is unsolved completely, it's been solved by certain people. When he presented that particular graph, this is the first time I just came to know about the Carey's equality and then other things. He was suggesting this sort of graph when he presented the upper part and the lower part. The upper part will become a lower part, this lower part of the graph and all these things. These sort of things he was mentioning there. And then immediately, I didn't actually hear what he spoke after that particular graph in the talk, rest of the talk. I just focusing on this particular graph. And it struck me that this is a typical combinatorial problem. This looked like a combinatorial problem to me. And then I don't know any background about who all working in that area. I don't know what is the basis behind that particular graph, how the captured data has been and medflies collected, all these things. This particular graph actually struck me, that particular moment. And then I just had something written on the paper, the proof, and then gave it to Jim the next day. And then Jim, along with, Jim asked me to prove it. I mean, he asked me to show the proof on the board. And immediately he told Ron was there, Ron Lee. And then they both thought that this could be a potential proof. Because I have not given a proof to them, because I just gave a sketch of the proof, because I didn't actually write the formal proof to them. Then I want to thank Ron also for that, and who also told Jim that I think whatever Arni showed seemed to be okay. So that gave a good boost, and then the main purpose of to go to the Nathan Keefe Symposium was to interact with the demographers and get to know what's happening, and then this gave a good boost to me to continue my work in demography. And that's how I started again, to look back to demography, classical demography. But before, when I was a faculty, full-time permanent faculty at Indian Statistical Institute, I taught demography. I taught various courses in mathematics, but I taught classical demography to really good undergrad math students. Then I read the Nathan Keefe's book. Yesterday I was telling Jim about, I read this Jordan's life contingencies. I taught actuarial science, other than other analysis and complex analysis, differential equation, along all these courses. I also taught the substantially mathematical demography and actuarial science. Then all these things I want to link up, when my proof to Jim became correct. Then the right and the Jim encouraged me. I want to go ahead and systematically study the population dynamics. Then this particular goal of this particular talk is to identify the linkage between the Carey's equality to population dynamics and Goldstein, Vaupel's contributions, and then back to the several centuries ago. I just wanted to see how the population dynamics look like in a century, 1,000 years ago, and then come back to the Carey's equality, and then the recent 30 years work on Carey's equality and related work, and then provide some new thoughts to the future, how this Carey's equality stuff can be applied to the future. And then just today morning before the talk, Dr. Ken Wachter gave me excellent ideas, how this life left can be applied to reproductive lifespan of women. All these things, and I'm going to look into that particular problem also after going back from here. And this is the overall structure of my talk, overall goals of my talk, and the structure of the talk look like that. I'm going to discuss the historical demography, a little bit from the Fibonacci numbers, Bernoulli, and then how stationary population, that they did not use the word of stationary population, but stationarity pretty much there in their work, Euler's work, and Alfred Lotka's work, Fibonacci, Bernoulli's work, and then I'll come to the Carey's equality and relevance, and beginning from the the Kim and Aaron's work, and then the Carey's equality, and then Vaupel's, Goldstein work, and then the fundamental, the theorem what we proved at Ohio, myself and Jim.
Just to note, we have to stop you at about 5 minutes to 1.
Okay.
Just so you know that we'll have about 40 minutes.
40 minutes time.
Yeah.
Thank you.
We'll have discussion after that.
After that.
Yeah.
Thank you. And then we will discuss the future implications of population dynamics. Yeah, this is the first available literature. What I find is on the population dynamics. And if you see that Fibonacci numbers, if PT is the number of pairs of rabbit population at the beginning of some month T, then P1 equal to 1, P2 equal to 1, given that P1 equal to 1, P2 equal to 1, and rabbits with at least 2 months old will be delivering an offspring, then Fibonacci found that PT plus 1 equal to PT plus PT minus 1. This as far as goes about 1,000-year-old equation. And then Fibonacci model is unrealistic in population dynamics. We all know that this is only for the rabbit population, and then the human population don't grow like that. But this is sort of first first population dynamics equation. Then coming to that, after given Fibonacci equation, this particular Fibonacci series of numbers, sequence of numbers, led to the golden ratio, which is another fundamental how the population dynamics actually contributed to the number theory. So golden ratio is one of the things where the undergrads learn about the number theory, and when they start learning the number theory, they also come through this golden ratio. And then you see that Daniel Bernoulli actually used this golden ratio to obtain these sort of expressions for the PT. For the population at time T, Daniel Bernoulli using the golden ratio, which obtained from the Fibonacci numbers, Fibonacci sequence of numbers, he obtained that. And then also, the spirals on a cone, they also observed the Fibonacci numbers, also the same as the spiral on a cone. And then patterns within a snail's shell, that is also the Fibonacci numbers. Fibonacci numbers come from that. People found out that is nothing but the Fibonacci numbers. Then after coming to that, I found that Edmund Halley, one of the astronomer royal at the time, he brought this equation, pk plus 1 is pk minus dk, which is where pk is the population size aged k and dk is the annual deaths age k at age k. Then Halley observed that the 5-year, based on the 5-year data from the city of Breslau, he assumed that number of births in Breslau during this period equal to the number of deaths during the same period, which is nothing but the stationarity assumption. This is assumption is stationary population, steady state population we call later period, steady state population or stationary population. But Halley never used that sort of terms there at that time. And then Euler went ahead and then he brought this sort of equation, pt plus 1 is 1 plus lambda times pt for all real growth, population, lambda is the population growth, which is a real number he assumed. When p0 is the initial population, pt plus 1 is 1 plus lambda power t plus 1 p0. This is what the Euler brought up, this equation, which is the model for geometric growth. So again, the population dynamics and geometric growth are related. That's how the population dynamics contribute for the geometric growth type of equations. And then, this is a hypothetical question. If the Euler asks, suppose Euler asks this sort of question, if a population in a region increases annually by 1/25th, and if initial population 1000, then after 100 years, what would be the population? This sort of questions Euler actually tried to answer, tried to put the questions and then he was trying to answer those sort of things. And then, 1760 paper in Euler, he also discussed about the births and deaths at time t, and if ak is the proportion of newborns who will reach age k, then using this sort of setup what we previously discussed, Euler brought down this particular equation where bt by pt and then product, summation of this one equal to 1. This is known as Euler's equation in population research, where lambda equal to the 0 in above equation. This is nothing but the stationary. This equation is one of the conditions for stationary population. But Euler did not use that word at that time. And later we will see that Euler's work and the Lotka, Alfred Lotka's work, Alfred Lotka gave a continuous version of that particular equation. So Euler derived a formula for the proportion of total population in that form. And this is now called stable population when the above proportion is constant. And Euler did not, that's why Euler did not use that kind of words at that time. And then coming to the Lotka's equation, for male birth bt at time t, survival a function at age x, and fx is the fertility function, survival function is fx and then the fertility function is hx. Then Lotka brought on this renewal equation, bt is bt minus x integral of bt minus x fx hx dx. When bt is b0 e power rt for a growth rate r, Lotka showed that this sort of integral equation, and then this can be obtained as a integral of e power minus rx fx hx dx is 1. So this equation is similar to the implicit equation by Euler in a continuous version. Now that particular equation we saw, this is a discrete version of whatever Euler obtained, is a continuous version of that particular equation. And then we all know that again the Euler and Lotka and Dublin, they found out this equation, and then when r star is greater than 0, if and only if they obtain Lotka's paper, he also obtained this sort of if and only if conditions. And then NT is the total population, again you see this sort of derivations in Lotka's classical works. Again, when this ratio bt minus x fx by nt as t tends to infinity, this becomes this particular value e power minus r star x fx by integral this integral. This is nothing but the condition of the stable population. Then William Feller, so Lotka has given this particular equation, integral equation, renewal equation, and then he has not rigorously studied that particular equation. But William Feller, who is one of the, I really admired William Feller's textbooks in probability. So he was at Princeton at that time, and William Feller actually rigorously understood these sort of renewal equations, and then he actually brought he contributed largely for the renewal theory. Although the Lotka, they have proposed it, actually brought into the pure statistical field, statistical discipline. because of William Feller's foundational work. Then you see that William Feller proved this integral equation of Lotka's type. Let us consider IID random variables, say T1, T2, that is identically independently distributed, non-negative random variables, where Ti is the lifetime of a component, ith component, or time between occurrence of lifetime events. That is, between two lifetime of a bulb. You change a bulb today, and then when you can change the next time the same bulb. That is the length of life, 100 days, 80 days, or whatever. T1, T2, Tn are the first bulb's lifetime, second bulb, third bulb, and so on. And then renewal equation NT counts the number of events. How many events? If your event is the life of a bulb or something, some duration, how many such events occur? NT is the renewal process. So anti-renewal equation where NT is 0 for T less than T1, because before you change your first bulb, there is no need to, you can't count anything. Whenever your first bulb got fused, you count them, first bulb, second bulb, and so on. So NT equal to 0 for T less than T1 before the first bulb, and then NT equal to max of N for T1, T2, Tn less than or equal to T. So suppose Fn equal to some function, probability Ti equal to N, if you denote that by Fn, this renewal process is recurrent if and only if summation Fn equal to 1, and this is transient summation Fn less than 1. These sort of results actually William Feller has brought based on the Alfred Lotka's contributions. That means again for the renewal theory also Alfred Lotka gave that the population dam, we saw the Euler's work and then Alfred Lotka's work, and then taking the Alfred Lotka example and bringing from that as foundation, William Feller brought further. He has moved this particular story of renewal theory, he took it further. And then this is just a simple background, we all know what do you mean by convolution of two equations, convolution of two functions, and we know that. And then after that, after that William Feller story, Alfred Lotka, all that, Ryder actually gave a proper definition of how he gave some conditions of how a stationary population look like. So he says that one essential condition of stationarity is integral of fx hx equal to 1, that is a maternity function and a survival function, whatever we discussed that integral of that is 1, where fx are defined as before. In addition to this particular condition, Ryder says that fixed survival function for males and females, population is close to migration, and fixed maternity function. Other than this particular integral equal to 1, these three conditions, that's what he wanted to say, Ryder, 1975 article in Population Index. So due to stationarity and due to stationary condition in the previous slide, the Lotka's equation becomes like that. Due to this condition, Lotka's equation Bt equal to integral 0 to infinity Bt minus x fx hs dx. So this is actually nothing but the moving average of the size of the preceding female birth cohorts. So Lotka actually brought down that as a weighted equation. And then after that, during the, after Ryder's work, Kim and Aaron, they published in Siam Journal of Applied Math, this particular equation, he brought an equation between that. This is also one of the earliest work on Carey's equality. This sort of brought a life left and life lived. This relation between these two, that sort of thing. Later, Goldstein, he also brought a similar result, which was actually this sort of equation. Kim and Aaron found out this sort of relation. Later in his Goldstein's work also 2009, he found out a similar relation like Kim and Aaron in the more demographic language. Where Sx is survival function, if you try to understand this equation, Sx is a survival function and Ex is expectation of remaining alive, conditional on survival to age x in a stationary population. Then you see that this is nothing but the life lived and this is nothing but the life left, average time, average life left, average life lived. Kim and Aaron in 1989. And then after a long time, I couldn't understand why actually Ryder has given some ideas and Kim and Aaron found it. Then after about 20 years, after that, this work, again the Vaupel and Goldstein, all it took some good amount of time. I mean, before Jim Carrey observed 15 years of time, and Jim Carrey, actually 1992 onwards, I think they have been working a lot of things on the life left, life lived. But I think that was going behind this thing from 1990s. But for the first paper published in 2004 by Carey and others, and then after that, I think it became again momentum for this particular life lived, life left concept, and then it actually carried forward. So if you see that the stationary population, this is what actually, this is what, this particular previous equation, if you see. So this is what the proportion of people, here at this, who are born, who are newly born, and then that is same as this particular proportion. This is stationary population, you see. In a US, this is a real-time US population. And the life table identity. This is based on this actually. I studied all the equations of Euler's work and then Lotka's work, all these things. I just try to link up these things. So these are one of the stellar contributions, one of the very profound ideas what Jim Carrey brought was that in stationary populations, the number of individuals who will die in a given duration of time is equal to the number of individuals who have lived exactly the duration. I think this statement I have took from the Jim Carrey's published work in 2008, that particular statement, and then later Vaupel has given a proportion. This has given in terms of proportion of individuals who live up to certain age is same as the proportion of individuals who will have that remaining life.
So, if duration is 60, what does this say? That duration is 60. It says the number of people who die in the stationary population in a 60-year period equals the number of 60-year-olds?
60-year-olds. Proportion of individuals who will have 60-year-old, who will have remaining 60 years.
Go back to your last graph. There, you didn't read that. So that fraction there, fraction of the population with exactly 85 years remaining equals a fraction of the population that's exactly 85 years old.
Yes, but that's a different statement than the next quote, which is all the people who have 85 or less years remaining. Those are the people who are going to die in the next 85 years, right?
Put your next slide on.
I don't think it's lived exactly the duration. I think it's yet to live, or remaining one.
Remaining one, yeah.
That's not exactly my statement.
Okay, it's okay.
Yes. Yeah. So this is after this observation. I think this is I thought I took it from Euler 2004, but it seems it is not that. It's not exact statement. Yeah. So this is again coming back to the first picture I showed. So this is what they observed. All these individuals, whose life is all the line. This is actually the time of observation. This is what they collect the data, and then they say that already, these many years if they live, hypothetical data already lived, and this is the time they're going to live, life left. And then rearrangement of that actually will become this particular population. This is like a pre-captured segment of that, and this is a post-captured segment.
Can you just say one more word? Is the top slide an empirical observation?
Yes.
Okay.
Well, empirical
Hypothetical.
from the computer.
Oh, it is
Hypothetical, yeah.
Okay.
Yeah.
So 2009, based on that, Jim Vaupel, he has brought this equality, Fa of A equals G of A. And then actually Jim Vaupel proved the Carey's equality. F of A equals G brought that, where F of A is a probability density function at age A, describing population age composition. And G of A is a probability density function at age A, describing the distribution of remaining lifespans. And then he termed the word Carey's equality, Jim Vaupel, in his paper in 2009, demographic research. He first time coined the word Carey's equality based on the Carey's observation in 2008, 2004, and Muller's work in 2004. All this, where Carey was an author, co-author, and then Carey observed this in his fly lab, in his fly data. And then Goldstein in 2009, he also proved a similar result to Kim and Aaron, what we discussed, the integral equation. And in Goldstein, he stated that life lived in a stationary population equal to the life left by the population at the same age. So this is also similar to the what we saw there, but in a different listing. So life lived in the stationary population equal to life left by the state population at the same age. The similar arguments can be found in renewal theory, Cox in 1962, if you see that book. And this also, I mean, the similar sort of arguments were there in the Cox book based on the renewal theory by the Lotka and then the renewal theory by the William Feller, all that Cox actually summarized in his book. And this sort of relation were there. And then as I mentioned, after the 1989s were Kim and Aaron, there was a long gap and I think people have not looked at that particular work, or maybe they are looking that was not published, unpublished, we don't know. But then again, 2004, when Muller published this sort of concept in his, with collaboration with James Carey, again this sort of results started interest to the demographers, and then Vaupel and Goldstein again that brought to the notice. So all this information I was not aware of actually, Kim and Aaron's work or Goldstein work or Jim Vaupel. James Carey, when I showed the results to them, and then James Carey told that this sort of results are already proved. When I showed the graphs, all these things, maybe you should look into the Jim Vaupel work and the Joel. That's how I came to know. I mean, I know them. I know their other work, Jim Goldstein work or Jim Vaupel. I know them, but I don't know this particular work. So he asked me to read this work, and then I have read those works, and then I got to know about a lot of work has been done in last 10 years about the life left and life lived, and then I found this sort of things which is completely out of the thing infection disease modeling I do. It's no relation to that, but it's very much attractive to me because this sort of results we can prove it without much influence of renewal theory concepts. That's what initially I thought, but later we modified it again.
We have about 15 minutes.
Yeah. So then coming to that, this is the main theorem what is proposed by May and Jim in after the Ohio meeting. The main structure of the theorem was already given that time, but we proved it. We actually rigorously proved after the meeting. Suppose we have a triplet of column vectors where x, y, z, where x is representing the capture ages, and y is the follow-up duration, and z is the length of lives for the k subjects or individuals, and fz is the distribution function of z which follows the stationary population, and g1 be the graph connecting the coordinates of sy, where sy is given like that, set of positive integers, and whose domain is nk. Let g2 be the graph connecting the coordinates of cx, the function of capture ages, whose domain is nk. And suppose cx star of minus j is xj, this particular xj, for all j, then script h be the family of graphs constructed using the coordinates of c star x consisting of each of the k star permutations of graphs. Then one of the member of this graph, this family, one of this member of the family is nothing but the vertical mirror image of G1. So this is nothing but this statement, this particular graph. So under what conditions, the summary of the statement is under what conditions this particular graph of this line would be one of the families of the graphs created from this. That is summary of the idea. One of the family of that becomes that. That is what this particular statement says. And then I'm not giving the proof, already it is available online. It came up in this thing, published last year. We proved in 2013, got access in 2014 and published in 2015. And then there also we gave the this particular graph we provided there, and you see the stationary population. That's what the phenomena what we observed, what was observed by the James Carey in his lab. You see that this is particular black part of the graph. This is nothing but becomes like that, and this is survival. The survival frequency, this frequency, and then this is survival again. You see stationary population, age distribution, and death distribution, and this is a captive survival. So they match the colors there. See that. And for non-stationarity, so parallelly while working with the Jim Carey, actually this is what I went to present at the Nathan Keefe symposium. So there actually I am looking into the non-stationarity of the population dynamics, how in the non-stationary population, how the population dynamic look like. So there we observed that in that particular article, 2014, it also came in 2014, each member of F star, F choose combination K star satisfies these two conditions, then this does not always lead to PN to stability. What is PN? PN is the population, global population, when a population becomes non-stationary, that means under non-stationary conditions, that means that's why you say it does not lead to stability. The Pn is the population global level, where A1, A2, AK are the k independent non-empty subsets of Pn, such that the cardinality of Pn is the integral of that, where F is the family of all the sets As, such that union of As is Pn, where Cn1 is number of births, Qm1 number of deaths, K star is size of the set such that this satisfies that. Then each member of F choose K star satisfies the condition. This does not always lead to Pn. So these two, one for non-stationarity, one for the stationarity condition, these two summarize the population dynamics.
Can we just go back to the statement? What does stability mean? Do you mean stationarity, or do you mean stability in the sense of stable population?
In terms of stable population.
So having the number of deaths equal the number of births,
Yes.
does not lead to
Stability.
stability. Okay.
So that there is implications of this particular theorem. So we discuss in three cases, that all three cases I am not discussing. So one is this is less than Cn1 greater than Qm, less than Qm and equal to Qm. So all three cases we discuss, and then how that that appear look like, that particular dynamics look like that. So one article came up in Journal of Math Biology, another article we published in Notice of American Math Society.
So can this picture help us understand the previous theorem? Can you explain it?
Yes. So you see that here, this is where the Cn1 equal to Qm1,
Okay.
this line, and Cn1 is greater than Qm1 and Cn1 less than Qm1.
Okay.
This look like that, for the Cn1 less than Qm part look like that, and this is the greater than, this is equal to. So all three cases we discussed there.
Okay. I'm trying to understand the statement where you say that the number of births is not equal to the number of it does equal the number
Equal
of
to.
deaths, but yet the population is not stationary.
Not stationary.
Is that shown in the
Not stability. So when the population births and deaths are equal, this would not lead to stability. This actually remains as a stationary condition.
I'm just trying to understand the meaning of your statement. What does it mean? So the green line is a flat line, right?
Yes, flat line.
Right. Do we call that line stationary?
Yes.
But you're saying it doesn't have to be a flat line?
It's a flat line because when this Qn1 equal to Qm1 under this condition, when t time, after certain time, t greater than t0, and then f minus f is not satisfying the condition. This part of f minus, those members are not satisfying the condition, and some members are satisfying the condition. That means if the total population is stationary, some part of the total population, if you sample from them, if they are not satisfying after some stage, then that total population would not be stability, would not lead to a stable population. So with the subpopulations, all the subpopulation would be stable, then only the total population will be stable. When subpopulation deviates from the stability, then total population will deviate from the stability.
Okay, thank you.
Yeah. So that was up to the Carey's equality understanding, and then the understanding basic structure of the Carey's equality and how the life lived and life left based on the Carey's results, and then the Goldstein, and then the Jim Vaupel, Kim and Aaron, and all this. We understood the basic structure of the population, life lived, life left. Then we thought that how do we use this kind of a tool to understand the age, to understand the age structure of age structure of some insects, age structure of some unknown population whose age reporting is not done. How do we compute that? So we are investigating in that direction, and then currently there is still unpublished work there. So what we are trying to do was we are trying to put that into each age of an individual who is being captured. We want to compute the frequency. We want to take the frequency of that individual and then age versus the frequency. We want to tabulate that each captured mosquito or each captured fly, how many such mosquitoes are there which are exactly same age, and then make that frequency and the age, one particular age. For each age we want to make a frequency, and we want to go for higher dimension for the Carey's equality. We want to see that what's going to happen. We haven't published it, but we're investigating the higher dimensional Carey's equality. How that look like? And then this is in that direction we are going, and just quickly.
Just can you give, what are the dimensions? What does higher dimension mean?
High dimension here, in one dimension carries equality. We are not looking the density of the each ages. So we are looking the density also we are adding to the carries equality, which is the density of that particular each age, each captured mosquito, each captured fly. The density we want to add into the carries equality and to see what's going to happen for that.
So one dimension is age. What's the other dimension?
Frequency or the density.
Of flies versus mosquitoes?
No, fly.
Of density of what?
Density of the age.
It's probability.
Probability.
Like so you don't know age for sure.
We don't know the age for sure.
Distribution.
What density each mosquitoes, what is the density of that particular age mosquitoes are in the living, and how many of them we captured.
So not just the expectation,
Not the expectation.
not just the expectation, but the entire
Density.
distribution. Okay.
So this is like we want to put into the functional data analysis, where just a line is important. You know, when in the functional data when we do, we translate the data into a function, and then we play with the function. So we want to now put that function into the system of carries equality, and then want to see that how this look like, how this could look like. And then we got some elementary derivation, where we obtained the, after the structure of this, I'm just skipping quickly. So we already given the structure, and then we rigorously, each age we rigorously discussed all that, the proportion to everything we discussed thoroughly. And then I'll skip the two theorems, their statements. So finally we obtained that, we obtained this expression for the Q, the probability of dying an individual. So all these things we have done it to obtain that Q part, that is the probability of dying of an individual during this time period. We are considering this kind of, the what's called the line, the graph line, only the density part and the age and density together we consider together, and then we wanted to construct the probability of dying, and in this we obtain this this particular expression where D is, this is again the Jim was suggesting that what happens if the truncation is done, truncation of the life left. So life lived and life left. So from the remaining life, if the data of truncated data is available, like if we know up to the 5 days of data we collect, what would happen? If we collect up to 6 days, what would happen? 7 days. So we are truncated from right, the information truncated from right, and we have to use that to obtain the total age distribution. That was the idea there. And then we also recently proposed two conjectures where we actually found nice results. We have not proved them, but we are in the halfway through to know about the carries equality further. That is if a population is stationary, then carries equality holds, but when carries equality holds, then population is either stationary or non-stationary in a population. That means life lived, life left will be life lived equal to life left. When population is stationary, we can observe that life lived equal to life left. But when life lived equal to life left in a captured population, then that population could be stationary or non-stationary. We observe from the data this is true, but then we want to rigorously prove it and to see that that we are this thing. And then the second conjecture is that suppose carries equality for a stationary population is suppose carries equality holds for a stationary population. Then carries equality also holds for all stationary subpopulations of that total population. And carries equality need not hold for all non-stationary subpopulations of the original population. This is second conjecture. So if carries equality holds for total population, we take some arbitrary population, and then carries equality holds for that. That is life left equal to life lived. Then all the subpopulations, if we take, then carries equality also holds for all the subpopulations of the holds for all the stationary subpopulations. Then if the total population is stationary, then there could be subpopulation of total population which is also stationary. Then carries equality also holds for that. But then second part is that carries equality need not hold for all the non-stationary subpopulations. If the total stationary population could be having non-stationary subpopulation, like if total population is stationary, then maybe age 15 to 19 age group may not be stationary. That particular population, that may not hold. So these are the two conjectures we are currently working. And then these are the results. When we try to plot the results for these particular conjectures, these look like that. You see the for stationary population, 85 years remaining, proportion of people 85 years remaining is same as 85 years here. And then 65 to 85 years is same as 65 to 85 years. And this is also for the for the non-stationary population. You see that this blue line here, fraction of age x in a population or fraction with x years to live. You see that is not matching here. See, fraction of x years just deviated where it is non-stationary. You see. Here's ongoing results.
I think you better skip ahead, you probably have about 5 minutes here.
Yeah.
Then we are trying to get the population life tables. So one of the applications we are currently looking is the population life table with Jim and Sarah. They are working together. On that I'm trying to, we three are trying to look into the, so one of the implications of Carey's equality is population life table, where we are trying to understand we are trying to mix the total population, because life table is synthetic population. And then we want to total population, we want to, 100 years population, there are several generations of population being into the added, contributed for 100 years dynamics. Then each population overlaps with the other population, the deaths, the longevity, the cohort born in 2000, say 1900, until they survive, they are actually overlapped with the various populations over the time. So we want to generate, population life table, where generation life table, how it look like. This could be one of the implications. While thinking on the Carey's equality too much into that, maybe this sort of population life table, generation life tables, or cohort of cohorts, multiple cohort, how it look like. All these things we are trying the current thoughts, Yeah, there are some references.
Thank you, Arni, and thank you for finishing so we have time for discussion. I know you had a lot on your plate and got through all of it. So well
Thank you.
Okay, so now we're ready for discussion. So I have an idea / question. Okay, so I've always thought about this in terms of kind of a thought experiment and the directionality of time. So imagine we have one planet where time goes forward, and we call the beginning of life birth and the end of life death. And we have another planet where time goes backwards, and we call the beginning the end of, we reverse the letters. Okay, so the result says you can't tell the difference, you can't tell which planet you're on. If we run time forward or run time backward and switch the labels, we have the same thing. And it seems to me that that's the definition of a stationary population. It's one in which time has no meaning. There's no discount rate, like in the growing or shrinking. And so it seems to me that there are many, that's just an alternative way to think about these things. So what
Time dependence. So
just time. You're just reversing time, and in the stationary case, we allow time reversal, and things must be symmetric. So it's a little bit like Einstein in the elevator or something like that. It's just kind of a thought experiment that in case that allows you to see what's going on. But I haven't developed it rigorously.
Okay.
Yeah.
So looking forward, it's very interesting, and then time. Same as that, we don't know. If I capture I always think that how they do experiment. If you capture a mosquito, suppose I capture a mosquito, how do I tell the age? It's or from where it has come.
Well, so to me, the amazing thing is not that this result holds, because we know from many different developments that it holds. The amazing thing for me is that there are all these applications. I wouldn't have thought, the two planets story, okay, I buy it, but I would have never thought that two planet story would enable us to know the age of a mosquito.
Yeah.
So that's for me, the applications is a really fascinating part of this, whereas I somehow have let the proof of the theorem kind of say, okay, that's established.
Yes, correct. I agree with you, because when I first time exposed to this particular result, naturally, I being come from the mathematical modeling background, I do try to model the various disease models, and then The first thing is understand the patterns. We need to understand the pattern of a disease and then how it spreads, how that when it stabilizes, disease stabilization, or Ebola, it came recently, for Zika. All these things when happen, that sort of mindset when I went to Jim's presentation. I mean, when I looked into the data, I already naturally excited about the way it is done, and then I wanted to look at a complete story, mathematically look into that. You see that each age, internal structure. One of the referee when you submitted, they said that the author looked like understanding both the authors. Each age they understand the internal structures of the population. All these things now. That's why the theoretical interest for us came up. How that will that lead to any new mathematics into that? Will that lead to any new ideas in mathematical stability theories? Like you see the previous. That's what I looked into historically. Whether anyone looked into that. So the theory also interests, and then, as you told, we want to look for real-time demographic application. We are really, really interested to apply to the labor forces. And today morning when I was discussing, Ken Wachter, he told fantastic idea about this really attracted to me to know how the reproductive span of women, given that lived life can be applied to the how many children are, what is the reproductive life remaining of a woman? Will that be equal to reproductive life already lived? Or the number of children, a proportion of children she will deliver in the future, will that be equal proportion of children? Is that a population stage? So this is a great application. Really strike me, and then he want to apply that sort of results. He's inspired to see whether that sort of things, how that impact on evolution, how that the evolution of the particular genes, whether before the reproductive span of a woman, she is some bad genes, she might reproduce to the new children, or if she already finished her reproductive span, if she has developed some bad genes in the body, she might not reproduce to the new children. This is a great idea. I would like to go back and then again put all the math into that and see how they look like. Yeah.
I'd like to ask a different direction question. When in the early and my captured data, one of the empirical discoveries that we probably didn't want was that there was evidence the captured mayflies were actually living substantially longer than within capture than those mayflies that had been reared entirely in captivity. So that those that had some time in the wild and came into captivity seemed to have an advantage. I don't think this has ever been explained. Remember when we put this out, Jim?
Of course.
We thought it
That's a
was
problem.
very exciting, but no one has picked up on it. Part of the analysis that went on in looking at that setting, where we're able to do experiments, you have those reared from birth in captivity and those reared after a time in the wild in captivity. The question arises, how do the relationships you've been setting forth translate when you introduce an unobserved inherent frailty into the model? And so in Vaupel, Ken Stelling's classic setup, you think that these flies are heterogeneous from birth on, perhaps with a simple multiplier, some with hazard rates higher, some with hazard rates lower. Now the population may still be stationary, but then the post-captive folks are enriched for lower frailty. Have you tried translating the Carey theorem or sophisticated route Carey theorems into a setting where you could have heterogeneous frailty across the divide?
No. I don't look into that, but yesterday itself, Jim was discussing about frailty. I know the frailty work, Philip Hogarth, one of the initial work of Philip Hogarth, a long time back, I just read his work on frailty models after Jim Vaupel's suggestion. The initial paper 1970, Jim Vaupel as a priority work, and then Philip Hogarth, one of the, he worked for Pfizer, and he wrote a book on priority models. So then I have not looked into that, but I would like to, and also planet example like time dependency. So these are the great thoughts, the time, when you look back, what would happen when you take it out, what would happen when we move the life left. So if this equality is true over the time period, what's going to happen to the population? If this equality is true for certain time of period, after that, when that equality is not, because the equality this is not a universal equality, we know that. This is not always true. So if the equality is true for a certain time period, and the equality becomes unequal after a certain time period, what would happen to the population? That sort of things like related to the, what can we say about total population? That's what we are thinking, Also we discussed about when the population is stationary, or the time period suddenly becomes non-stationary. So with that particular time when it becomes non-stationary, the time of points of inflection, can we say something about that? So then I will also definitely look at the priority thing here, priority part, and then I currently have not looked at seriously the impact of priority onto that. I mean, mathematically we thought about that, we looked at the graphs of mortality, priority, age is a big important, big thing for priority.
I'll make it clear that when he says, puts that math up there, he says we, it's him. But, just to put this in context, the whole motivation here was, here we are in demography. But imagine if you didn't have age. Demography without age is just simple population modeling, non-age structure and so forth. And so you take it for granted, as demographers, you always have age structure. But in ecology, especially insect ecology, you have no clue what the age is. And you can do mark recapture, but I always say you release 10,000, you get 5 back. It's like releasing minnows into the Atlantic Ocean, never to be seen again. And so the whole motivation was to come up with a way to do estimate age structure, so then you can do real demography. That was the motivation. And but what Arni's presented here, I mean, it's a lot of math, so it's good mathematical, for a mathematician, it's really interesting. But on the other hand, we're looking for what is it? It's like your application, and it can't be just insects. Is that we're looking for relevance to new ways to look at human populations in particular. And for that matter, that's where you can get funding and so forth. You're not going to get, biodemography is sort of dried up, basically. It's kind of bone dry, actually.
Is a key assumption in this, to make this all work, that the age and capture, that the capture itself is independent of age? So if we do something like prisons,
Yes.
where we know that people's likelihood of entering prison is different at different ages,
Yeah, sure.
we wouldn't expect this to work. But if we were,
It's not that.
No,
it's
but it
based
could be a time in prison, or so that age can be, the vertical axis can be age and time in
Sure.
prison, that sort of thing.
if we're randomly sampling people who go to prison, we randomly sample people today,
Yeah.
then their future time. But the capture itself is
There's no age bias.
doesn't have an age pattern, but one could certainly
No, you could get all that.
yeah.
But look, I mean, even beyond the stationary case, we're looking, Arni didn't have time to get into it, but the population life table is what we're calling it. I presented at a PAA about 5 or 6 years ago this concept. It's basically cohort to cohort, so that you capture, that is mark, or take an entire population, you call that a cohort, and survive them forward. Are there new properties of population level analyses, population rather, aging or whatever, that would emerge from that kind of analysis? That's an extension of this, sampling from a whole population, and without the stationarity assumption. And in fact, this is what Sarah's going to be working on, is that you look at the population level, do a life table of everything captured out there, and see if you can look at the usual parameters of QX and EX and DX and all that, and make sense of that. Because there's no way that you can get at age of insect populations. And so anyway, that's one of the applications we're exploring. But I'd like to, we're looking for applications in human populations as well. New ways to think about populations
Yeah.
in general.
We still have time for a couple more questions? Maybe not for answers, but certainly questions. Okay, well then let's stop here. Thank you so much.